This lecture is going to give you a little bit more details of how we plan to link some of the more high-level reasoning about this web server that is the main demonstration vehicle for the technologies that we develop in the DeepSpec project to across the various verification formalisms. So starting from a high-level sort of client-side specification about abstract network packets, ideally all the way down to the verified processor. Now this is still very much in its infancy, this project, so this will just be a snapshot of where we currently are, and you will agree with me that there's a lot more work to be done. So before I start, Benjamin already at the start of his lecture mentioned who is currently working mostly on this verified web server sub-project, and in particular these three graduate students at Penn have been doing most of the implementation work, assisted in particular on the EST side at Princeton by William Munsky, who is just starting a assistant professorship at the University of Illinois in Chicago early September, so he's in the process of moving. And some of you actually may have met him last week here, and some of the, all of the students, almost all of the students are also here, so you can ask them questions when you're out. And from the Yale side, we've mostly been interacting with Wolf Honoré, who's a graduate student over there. So, as you will remember from Andrew's overview talk and also from Benjamin's introduction, this DeepSpec web server is intended to serve as a demonstration vehicle for a lot of the technologies that we're developing. Not all of the technologies, but we thought that it's very good to have one capstone application where we can showcase the formalizations and verifications that we develop. And our rough architecture of such a web server is like this. So we want to, of course, want to exploit that everything is running on a verified operating system or hypervisor kernel, in fact, underneath with verified hardware underneath. And one of the properties that we get from running on a verified operating system is that we can have isolation between different hypervisor partitions, so we can indeed separate in a more trustworthy way different applications that run in different clients, not all of which necessarily have to be verified in the first instance. So even, for example, an unverified TCP stack that connects anything that the web server, any connections that it makes with the internet, will not be able to corrupt any of the code running in other partitions. That's one of the guarantees that we get by using Certicos or similar hypervisors. As Andrew mentioned already, one of our motivation applications is not so much a web server that you interact with typically over the internet, but one of these embedded web servers that occur, for example, in routers where they allow you to make configuration changes. And that means that the web server is in particular, in the end, implemented as a library, typically here in C, which can be called from other application code. Now, components, so I'll be mostly talking about roughly this part here. We intend later on to have connections to some storage system for storing pages that are served, or even updating data in a system. So this is sort of a nicely isolated project, but that is clearly motivated by this. And we're still in discussion sort of which exact configurations we are going to use here of communication stacks, and which of those we are going to verify. All right, so what are the main challenges? Well, none of these components are exactly small. So we've already seen that formalizing models of these systems might help beat us the complexity, but still that is a challenge. The interfaces between all of these components, for example, just between C and an operating system, are not really well specified in the formal sense at present. So one of the challenges that we're facing is, for example, to give precise specifications of operating system calls that can be assumed by a VST proof and can, on the other hand, be materialized and guaranteed by the Certicos operating system. And we'll see one or two examples of that in the talk. And also, some of those specifications concern more the internal view of systems, but how to match them up with externally visible contracts is also still not quite clear in some cases. And of course, some communication just isn't exposed to external users. So what I'll be discussing today is a small selection of topics, or one particular topic in particular, and that concerns how to specify and verify code in VST that will sit somewhere there in the server component, but makes calls to, in the end, the outside world, but typically via either an OS call or some other message sending and receive primitives. Yeah, Zach?
Sorry, I just want to make sure I understand. Earlier you made a comment. So are the components, like the crypto and the TCP stack, are isolated? They run in separate?
They could typically run in isolated components. Once you've verified them, you can also include them in other configurations. So the system architecture is still a little bit in flux.
So if things have not been merged in the same component, how do they interact?
Typically by OS calls.
So the HTTP server will be able to make a call to the OS to get crypto services.
Yes.
And that will be satisfied by this other component.
Yes.
Okay, cool. Got it.
Okay, so and in particular, that means we need to specify in the end some OS primitives for sending and receiving network packets or messages, and the way these specifications will be done will be that we need to link model level specifications of these interactions at high level in Galena to low level code specs in VST. And we do that, of course, you will have guessed this, by using these interaction trees that Benjamin introduced in one of the Quick Chick lectures. And here's a simple example. So I'll have the COC type as a reminder on the next slide, but you will remember that these are essentially sort of representations of the potential computations that a system that interacts with the outside world can make. So there are visible actions that we may want to partition further into input and output actions. There are silent actions, here indicated in green, these tau actions. There are terminal actions where we just get back with a reply to the outside world and stop interacting afterwards. And the behavior of systems can in principle be infinite. And that could be silent or interacting. So this is the COC type for these interaction trees, which you'll also remember from Wednesday. So it is a type, a co-inductive type, represented the potentially infinite computations. You remember that it's a monad. That gives us nice structure to compose things. We parameterize this monad with this type of events, functions over types. And we have an additional type parameter here, which is x, which is the type of the eventual return values. So there are three constructors. These are the terminal interactions. So we just return a particular value of that type x. Then we have the visible interactions, which take an arbitrary event parameterized by an additional type y. And then, in particular, if that event is one that provides input back to us, there's a continuation here which can depend on that return value. We will typically select the type y to be unit when we don't expect return value, so particular for output, and for useful input, y will be typically not the unit type. And then we have the tau constructor that is just another continuation wrapped in this explicit constructor. And again, just as a reminder, given this structure, we indeed could prove that it satisfies the monadic laws or small variations of those, and we can construct particular sort of useful other operators that, for example, ignore some input, they lift an input, an event actually, to a visible input, which just does that single step. We can define infinite computations that silently diverge, or here other infinite computations that carry out an arbitrary event x and then loop forever. You saw them all on Wednesday, I believe, or if you go back to this slide, you will find them there. So this can all be defined, and we will make use of some of those in the rest of this talk. So the question then is, how do we link these interaction trees to C code so that we can refer to them somewhere in specifications and verify programs that make such interactions using the VST, and particularly that means how shall we specify the primitives in the OS that actually realize these operations again in the OS. So I will shortly explain you how we do this, but in a nutshell is that we introduce a particular new separation logic predicate, and then which we can mention in the pre and post conditions of both the OS actions and then of programs, application programs. And we will discuss two small examples. One is just indicates or illustrates interaction using getchar and putchar. So that's character I/O, and then I'll discuss a little bit more what we've done with this small variant of the web server, this swap server that Benjamin introduced already on Wednesday. Okay, so here's the gist of the idea. We can define a novel separation logic, so spatial predicate called interaction tree, which essentially gives us the ability to embed an arbitrary tree in the SEP clause of a VST specification. And by doing this in the SEP clause, it is guaranteed that this representation of the tree cannot be just duplicated. This essentially means that the access to the tree is just a resource in the same way that access to memory locations in the heap are regulated by the separation structure that underlies the VST logic. So we can then in particular specify and verify functions like this, where we have an I-tree predicate, say, for a sequential composition in our precondition, and that sequential composition carries out some event, binds its result using the monadic bind operation to some value R, and then has a continuation K that depends, of course, on that R. And by making this the step here that corresponds to the event E, we will have in the post condition just the I tree represented with K of V, where typically the V is here existentially quantified, and you may further specify its properties in the other parts of the post conditions. Now you will see here that we model this progress of I-trees in a forward direction. So we start essentially with a description of what the program is permitted to do, and there sort of the entire sort of computation tree is laid out without specifying exactly which path we take through that tree, and that is further then sort of refined as we proceed. So this is the consuming style rather than building us a sort of a constructive style where we would sort of monitor or build up a trace of events that have happened. And this alternative sort of the more complex terms would show up in the post condition. But this is a little bit more similar to well-known ways that sort of process calculi operate. It also simplifies the treatment of these bindings because typically when you see just a sequence of a couple of input values and output values, if you just create a trace, then it's not so clear which output value, whether an output value of 3 was just emitted because the program said I want to emit 3, or whether it referred back to some input. So this binding that we get from the monadic structure is maybe slightly easier to model in this forward way. And also this permission to carry out these options even interact a little bit nicer with a partial correctness interpretation of the logic that we have in BST. All right, so I'm not going to go very deep into the semantic foundations of this, but the essence how this predicate can be justified is that BST has a very general notion of ghost state, and in particular of ghost state for which you can restrict how it is shared between the program and the environment. And that is this has X'd predicate, so it's an mpred, which already indicates where we're going to use it in the SEP clause of the logic. And this definition, which is actually pretty short, but if you want to understand it, you have to dig through lots of VST code, says that there is a certain ghost location that stores this value, oracle of this arbitrary type Z, and that the ownership is shared such that it can be read by the code, and in particular our sort of code specifications and the external world, including the OS, but it can only be modified by the external world. And that means that when we specify now a send or receive, then only the OS calls can move the world forward, and we can internally only consume that. So a quite natural idea then is simply to define this I-tree predicate of T as an has external behavior of T, so specialize the type Z there to the I-tree type and aura with T. And then we get essentially what I was just outlining, that the external world moves the protocol forward, and we embed the tree reductions in the external calls. So let's look at how that looks in more detail. So here is a simple I-tree that just allows us to do simple I/O. So we have two actions, reading and writing. Reading just returns immediately and gives us back an integer, and writing takes an integer, does an interaction, and then doesn't return us a return value. So the type there is unit. We can even define some nice syntax for that as shorthands, and then we can use the general construction of the interaction trees to define our I/O trees, which are exactly the general tree constructions instantiated with this I/O event and maybe with overall return type unit. So the last thing is that we will write something. Questions so far? Okay, so then how do typical specifications look like? Well, here are for two somewhat simplified specifications for getting a character or putting a character. So we will include the write C followed by a continuation K in the precondition of the put instruction, and in the return we will have just that the tree has consumed this one action. And indeed, if you look at the specifications of put character in Linux, you will see that indeed the value is also returned as a return value. For getting something, we will use, of course, the read primitive, and our continuation may depend on that R. So indeed, here in the post condition, we will have an existentially